Implicit differentiation. You heard me say the word a few times. Basically what we're going to do is we're going to take an equation that has functions in it, and then we're going to differentiate the whole equation. We're not going to just take the derivative of a function. We're going to have that function already embedded in an equation. Okay, so when we have something where, say, y is some function, we do that explicitly, and that's everything that we've done so far. You know, we've had something like this where we say, okay, here's our function, take the derivative of this. What we're going to do now is sometimes we have these definitions that can't be expressed necessarily as just y equals something, like this one, x squared plus y cubed minus 2y equals 3. You can't solve that for y. You can't say y equals and then some other expression. But we have this relationship that's a perfectly valid relationship, and we do want to be able to figure out rates of change with that. So if I were to take this function, it's not really a function, it's a relation, and it looks like this. It looks like, I don't know, what do you think that looks like? Maybe a jellyfish, an octopus, or something of that sort, you know, a profile of that. But there's all sorts of wild curves, and just about anything you can draw, there's some equation that goes to it. So if we want to find the derivative, let's say the rate of change at any particular point, we'd need to be able to take derivatives of things like x squared plus y cubed minus 2y equals 3. So we call that finding the derivative implicitly. Now, also imagine this point where x is, and see it's not a function because x has another value down here, and in fact, there's probably some point where the derivative is the same at both of these places. So not only do you have two values of y, you have two values of y prime for any given value of x. So it makes sense that if you don't start out with a function, that your derivative doesn't necessarily have to be a function, it's a relation as well. But the derivative still describes the same thing. It's the rate of change of y with respect to x. Okay, so let's use this. I'm going to use the differential operator, the d over dx. And so something like this that you already know, if I just take the derivative of x squared, I know that that's going to be 2x, right? That's a derivative you know. If I take the derivative of just y, all I get is the derivative, y, right? dy dx. So there's nothing earth-shattering here. But what if I want to take the derivative of y squared? Okay, so here we have to use the chain rule, right? Because the outer function is the squared function, the inner function is y. And so let's use the chain rule on that, and so we find that it's 2y dy dx. Now this is the hard part about this. As you see, in the very first derivative I show you, you have the derivative of x squared is just plain old 2x, but the derivative of y, and here's the thing that you have to remember, it's the derivative of y with respect to x. We have 2y, which is the ordinary derivative of y squared, times the derivative of y, which is dy dx. Now why don't we do that up here? Well, in fact we can. We can say 2x times the derivative of x. How does x change with respect to x? dx dx is 1. Okay, so it vanishes on us if we have the same reasoning that we apply when we're taking the derivative of x with respect to x versus the derivative of y with respect to y. Okay, so we never really have calculated the derivative of y, so to speak. We've calculated the derivative of y squared, and it's now in terms of y and the derivative of y. Okay, so this is the chain rule. And like I said at the beginning of class, implicit differentiation is entirely an application of the chain rule. Okay, so let's take something like this, where we have dx, or we're taking the derivative of x times y. All right, we're going to use the product rule here. we're going to take the derivative of the first term, which is dx dx, multiply it by the second term, and then we're going to take x times the derivative of the second term, which is dy dx. And if I simplify that, I get y plus x dy dx. Okay, so any questions on that one? This is a really important example, and there's almost no words to describe it other than what I've said. We're using the product rule to disassemble this derivative of x, y, and so we get y plus x dy dx.
I guess I don't understand how dy over dx is being used as an operator. Like, I don't understand its purpose.
The d over dx?
Yeah, or like the notation itself.
Yeah, we can use an alternative notation as well. What that essentially is I'm going to say what this means is take the derivative of this expression with respect to x. Okay, so take the derivative with respect to x is one way to think of that operator, and then we write dy dx as the derivative is the derivative of y with respect to x. Okay, so that's one way to look at it. The other way to look at it is if we use prime notation, and here I'm going to really simplify prime notation a bit. I can say I want to take xy prime, okay? So then this is going to be x prime y plus xy prime. The derivative of x with respect to x is just 1, right? So we have, again, y plus x y prime. And most people, when they're doing implicit differentiation, they prefer this kind of notation because it's a lot simpler. You know, you're not writing dx very much, you're just writing a prime, and you just make sure that this prime stands for the derivative of all this. What you lose in this is the fact that you're taking the derivative with respect to x, okay? And so this notation is a shorthand because you're already assuming that you know which derivative you're talking about. If you're taking the derivative of this with respect to y, of course you get exactly the opposite. You get x plus y x prime. That's the derivative with respect to y. But for us, we're always going to be looking at the derivative with respect to x. So when we say something like this, what we're really saying is the derivative of x of f with respect to x. Just like you're evaluating the function at x, you're also taking the derivative with respect to x. And so this notation retains that. What doesn't retain the notation is if we just use f prime. And so there we have to understand from the outset that we're finding the derivative with respect to x. Okay, so that's why I'm using this notation here, this dx, just to keep reminding ourselves that we're taking the derivative with respect to x and not just some derivative, okay? Because then we either have to retain the x prime or we have to define what y prime is. And so with this, it really describes it more fully. Okay, so product rule. Okay, so let me go through a couple examples. This x squared plus y squared equals 25 is a circle, right? Circle of radius 5. And we know that the point 4, 3 is on that circle, right? Because 4 squared plus 3 squared equals 5 squared. Real basic. Okay, so let me take the derivative with respect to x. Okay, so I'm going to take the derivative of the left side, and what I get is the derivative of a sum is just going to be the derivative of each of the terms in the sum separately. The derivative of a constant is 0, so this goes away to 0. And then if I take my derivatives, the derivative of x squared is just 2x. The derivative of y squared is going to be 2y dy dx. Okay, so there's my expression for the derivative, and that of course equals 0. Now, what I want to really find though is the derivative of y with respect to x, and so I'm going to solve for that. I'll subtract 2x from both sides, and divide both sides by 2, and then divide both sides by y, and so I get my derivative is going to be the ratio between x, which in this case is 4, and y, which is 3. So I can find the slope of this line right here. The slope of this line is -4/3. Okay, so think of what a slope of -4/3 looks like. It's going to slant from the upper left to the lower right, and it's going to be a slant that is more than just 1. It's going to be a little steeper than 1. So at least from a sketching standpoint, it looks like that would be a pretty good number. Now, that's not just the derivative at x equals 4, that's the derivative everywhere. So let's kind of go around the circle and see what we get. So when x equals 0, y equals 5. And so the slope of this line that's tangent is going to be horizontal, so the slope is 0. So sure enough, 0 over 5 is 0. Now if we have a vertical line, that's an undefined slope because the slope can't be expressed as a dy dx kind of deal, right? It's a matter of if we're going to find x equals 5 and y equals 0, we're going to have division by, we're going to have division by 0 if we try and actually compute a slope. And that's the same thing that we get here. If we say if x equals 5 and y equals 0, then that's a vertical line because it's an undefined slope. Okay. So take another point, like it's not a function, so there's two values of x that satisfy that. So here we have x equals 4, y equals -3. That would be right down here. If we calculate the derivative there, we get 4/3. And in fact, that at least quantitatively looks the same, or qualitatively you would expect this outcome, right? Where you have a positive slope, it goes from the lower left to the upper right, and it looks like it's a little steeper than 1. So 4/3 is a little steeper than 1, and it's positive. Okay? So the thing about implicit differentiation is that we're going to find the derivative of the whole equation, but then we're going to solve for the derivative of y. So just like in here, when I took the derivative of both sides, I didn't stop here. I'm solving for dy dx, and so I have to rearrange everything, and I get some expression in x and y. Notice that there's no derivative on the right side. There's no dy dx on this side. We have just a single expression, derivative of x, or derivative of y with respect to x is the ratio of x over y, the negative ratio. Okay, another example. Let's say we have, revisit that very first polynomial expression that I was looking at. So how do we do the derivative here? So if I take the derivative of both sides, I'm going to do this by term. So the derivative of x squared is going to be 2x. The derivative of y cubed is going to be 3y squared dy dx. And the derivative of -2y is going to be -2 dy dx. Right? If we just have a coefficient times y, the derivative of that is that coefficient times the derivative of y. And then the other side, we have a 3, so the derivative of 3 is 0. And now what I have to do is solve for dy dx. Now here's where your algebra skills will come in. First thing I'm going to do is subtract 2x from both sides. Then I'm going to factor out the dy dx and then divide this expression in parentheses and we get dy dx equals negative 2x over 3y squared minus 2. So here's going to be your basic strategy in finding this. You're going to take the derivative of each term, and then what you're going to do is make sure that every term that involves a dy dx is on one side and everything else is on the other, and then you're going to factor out this dy dx, and then whatever factor is left over, you divide both sides by that, and so you get dy dx equals that expression there. Yes?
So why isn't it like 2x dy dx? I mean, dy over dx plus 3y squared. Like, why is it only on the 3y squared and the negative 2?
You're asking me about how this factored?
Oh, the one above it.
One above it. Why is that 2x?
Yeah. Like
You know the derivative of x squared is 2x. The derivative of y cubed is going to be 3y squared dy dx by the chain rule, because we're taking the outer function is the cube, and so I'll take the derivative of that, which is 3y squared, and then the derivative of y is dy dx.
But why doesn't 2x have dy dx?
There's no y in x squared, so if I were to apply the chain rule here, I would get 2x dx dx, which is 1. Okay? Okay, so here I already mentioned the strategy, but I want to write this out so you have it in your notes. Okay, so one of the things that you can do is you can use y prime instead of dy dx. Save yourself some writing, and just like this, you know, it simplifies the notation a little bit. Okay, so you may use that. So what you want to do is you want to make a rational equation into a polynomial. What I mean by that is that if we have something like this, where we're taking, you know, something like 2y equals 3x plus y over, let's say, y squared, you want to work this until you get a polynomial like 2y cubed equals 3x plus y. So you want to get rid of all your denominators, in other words, because getting rid of your denominators allows you to use the product rule and the chain rule exclusively without getting into the quotient rule. Okay, so here's avoiding the quotient rule with this is actually pretty beneficial. So here's another example. If I have x plus y over xy equals 4, I want to make that into x plus y equals 4xy, because that only involves using the product rule, not the quotient rule, like you would have to do here. Okay, so then you do this carefully, and so if I'm going to take the derivative of this now, the derivative of x is 1, the derivative of y is y prime, and then this derivative is going to be 4x. Well, the derivative of x is 1, so we have 4y as the first term, and then we say 4x y prime. So this is the application of the product rule. So we have 4xy equals, the derivative of that is 4y plus 4xy prime. Okay, everybody see that? You would expect with the product rule with something like 4xy that you get something nice and symmetric, but you don't, because we're not taking a derivative that's necessarily symmetric to that. What we're doing is we're taking a derivative with respect to x. So the first term is going to be the derivative of 4x is just plain old 4 times y, and so that's the first term. Then the second term is we're going to keep the 4x and take the derivative of y, which is just y prime, and so we get that second term. Okay? And then what you want to do is move all the terms with a derivative to one side, everything else to the other. Okay, so what I'm going to do here is I'm going to say y prime minus 4xy prime equals 4y minus 1. So you see what I did. I kept this on the left side. I moved this 1 over to the right side. I kept this 4y on the right side. Move the 4xy prime, since it has a y prime. Move that over to the left side. And now you factor out the y prime. And then you solve for y. So what I'm going to do is I'm going to factor out the y prime. So I get 1 minus 4x times y prime, and then divide by 1 minus 4x. And so I get y minus 1 over 1 minus 4x. And there's my derivative of y. Okay. I'll give you another example here. I want to find y prime with this, this expression xy plus y squared equals x squared. So I'll go over the steps again. So the first thing that we want to do is we want to make sure that it's some type of polynomial expression, not a rational expression, and that already fills the bill, so we don't need to do anything there. But now I want to take my derivatives. X times y is, we take the derivative of x, which is 1, times y, plus x times the derivative of y, which is xy. So there's our derivative of xy. Now we're going to take the derivative of y squared, so that's going to be 2y y prime. And then we're going to take the derivative of x squared, which is just plain old 2x. So the next step then is I'm going to move everything that doesn't have a y prime to the right and keep everything that has a y prime on the left. And so here we have that, so we can factor out the y prime, and we get x plus 2y in parentheses times y prime equals 2x minus y. And then we have y prime equals 2x minus y over x plus 2y. Okay. Everybody okay with this? So the next thing for you to try is doing this on your own. I'd like you to try and find the derivative of x squared minus y squared equals 4. Anybody recognize what this equation is? Remember, if we had x squared plus y squared, we equals 4 as a circle, but what's x squared minus y squared? Just to try and visualize what you have. No? Good guess, though. It's a hyperbola, okay? So an ellipse would have unequal coefficients between the x squared plus y squared. And then when you take the difference between an x squared and a y squared, you get a hyperbola. Okay, so go ahead with that. I'm going to start passing out some papers. We have the derivative of x squared is going to be 2x. The derivative of negative y squared is going to be 2y y prime. The derivative of 4 equals 0. Put everything that doesn't involve y prime on the other side of the equation. Divide both sides by negative 2 and then by y, and we get y prime equals x over y. Okay, any questions on this one? Okay, so another one here. Yeah, sure. Okay, are we good? All right, so another one for you to try. Okay. How do we do? Okay? All right, so here it is. So, the product rule is going to play into here. So we take the derivative of x squared, which is 2x, and multiply that by y squared. And then we're going to add x squared plus the derivative of y squared, which is 2y prime. The derivative of negative 2x is just negative 2. The derivative of 4 is 0. The derivative of negative 4y is negative 4y prime. And so next step is collect everything with a y prime on the left side. So that means this one's going to the right, this one's going to the right, that one's going to the left. I'm going to factor out my y prime and then divide by that remaining coefficient. And there's my derivative. Okay, so the steps are pretty well set out for you. You take, you make sure that you have some type of expression that doesn't have any ratios in it. Take the derivative of each term and make sure you're applying the product rule properly. Gather all the y primes to one side, factor out the y prime, and then divide by that coefficient, or that one factor that you get that's multiplying the y prime, and then you'll get a ratio. Okay, so here's the last one. And since we have only 3 minutes left, I'll just walk you through this, okay? Think about this as I go along, though. What I want to do is make that x and y separate, so I can... A couple ways I can do this. I can use the chain rule by applying the chain rule on the square root and then take the derivative of xy, or I can separate this out into the square root of x, square root of y. And so I get, by the product rule, the derivative of x, the square root of x is 1/2 x to the negative 1/2 times the square root of y. Then I'm going to keep the square root of x and take the derivative of the square root of y, which is going to be 1/2 y to the negative 1/2 times y prime. And then the derivative of negative 4y squared is going to be 8y y prime. Derivative of 12 is 0. So I'm going to rewrite it as all with square root signs. I mean, you may choose to do this at a different way, or put it all into fractional exponents. That's okay. But I'm going to move the that first term that doesn't include a y prime to the other side. And now with this expression, I'm going to factor out the y prime. And then I'm going to divide both sides. So I get my answer that looks like this.